Okay, our final talk of the conference is by Dan Petersen, and the title is Lie, Associative and Commutative Quasi-Isomorphism.
Okay, thanks a lot for the invitation. It's an honor to speak here. And given that I'm the last speaker, I also have the privilege of thanking all of the local organizers. It's been a really stimulating and mind-expanding week, and everything has been organized very smoothly, and I suggest we give all of the local organizers a big round of applause. And I've been to Uppsala for mathematics, but I haven't been to this building before, which is an extremely nice building, and it's quite famous in Sweden. And I think the most famous thing about it is if you come into the main hall, there are these golden letters. The first thing you see, and it says in Swedish, tänka fritt är stort, men tänka rätt är större, which in English means to think freely is grand, but to think correctly is grander. Maybe all of you have had this explained to you at some point by a local during this week already. And it's a very controversial message, of course, and people have said, oh, this is terrible, it's embarrassing to the university, you have to change this. It is fascism, and the greatest ideal in the university should be thinking freely, obviously. But I think it's very appropriate for this week, because it sort of symbolizes the meeting of mathematics and physics. Because mathematics is about thinking correctly, and physics is about thinking freely. And some people can do both. So I will talk about some joint work with Ricardo Campos, Daniel Robernicon, and Felix Wierstra. It's at string math. There will unfortunately not be very many strings. There will be some math. So I'll start with a warm-up here. So G is a Lie algebra, and UG is the universal enveloping algebra of that Lie algebra. And here's a question. If I know the universal enveloping algebra, can I recover the Lie algebra? And I think everyone here knows the answer in one form or another. So this universal enveloping algebra is not just an algebra where you can multiply things, you can also co-multiply. It has a co-product, which goes from UG to UG tensor UG. And you say that an element is primitive if when you co-multiply it, you get x tensor 1 plus 1 tensor x. And it turns out that there's this compatibility between multiplying and co-multiplying, which implies that when you take the commutator of two primitives, you get a primitive again. And that says that the primitive elements actually form a Lie algebra. And now there's a Poincaré-Birkhoff-Witt theorem, which implies that when you map G into UG, the Lie algebra homomorphism, and it takes G isomorphically onto the Lie algebra of primitives. So the answer to the question is yes, you can recover G from UG, and what you do is you take the primitives. So you can make the question trickier if you want to, because that answer assumes that we know UG as a bialgebra. But what if we're just given UG as an associative algebra? Maybe someone hands me an associative algebra presented by generation relations. They tell me this is actually the universal enveloping algebra of something. What is it? What do I do then? So here's a formal version of this question. If I have two Lie algebras, I assume that the universal enveloping algebras are isomorphic. Must G and H be isomorphic? And when you hear this question for the first time, your natural reaction is to believe, well, either the statement is not true, you cannot recover the Lie algebra. In that case, there are probably easy counterexamples. Or it is true, and then there's an easy argument. You don't expect this to be an open problem. But until recently it was. But the spoiler for the talk is that the answer is still yes. You can still recover G from UG, even if I'm just given UG as an associative algebra. And the way we came to the question was very roundabout from rational homotopy theory, and I will start in a completely different end of the project somehow. So let A and A prime be super commutative DG algebras. And I put super in parentheses because I'm not going to use super anymore. So whenever I say commutative, I mean commutative in the graded sense. So odd elements swap past each other and get a minus sign. And I say that a morphism of DG algebras is a quasi-isomorphism if the induced map between the homologies is an isomorphism. And I say that A and A prime are quasi-isomorphic as commutative DG algebras if there is a zigzag between them like this. So I can go to A from something else, and then from that thing to something else, and so on, back and forth. And all of the maps involved are quasi-isomorphisms. And I write that as A, I don't know what to call that symbol, A prime. And this does not imply the existence of an actual quasi-isomorphism from A to A prime, which is important. It's just not true that there will be a map from A to A prime inducing this quasi-isomorphism. And this was for commutative DG algebras, but the definition makes sense for any kind of algebra. For DG Lie algebras, DG Hopf algebras, so whatever algebraic structure you can think of. And now, let's suppose I have two commutative DG algebras. That means that there are a priori different notions of what it means for them to be quasi-isomorphic. If I say that they're quasi-isomorphic as associative DG algebras, that's not necessarily the same as saying that they're quasi-isomorphic as commutative DG algebras. Like I gave this very wordy definition, quasi-isomorphic as commutative DG algebras. The point here is that in this definition, I'm insisting that everything in the middle here commutes. All of the algebras are commutative. But it could happen that, A and A prime are commutative. There is a zigzag like this where things in the middle are not commutative, but there is no zigzag where the things in the middle do satisfy commutativity. That's also a natural question. Is associative quasi-isomorphism the same as commutative quasi-isomorphism, or are the two notions different? And our first main theorem is that there is in fact no difference in characteristic 0. Everything that I will say is exclusively in characteristic 0. So let A and A prime be commutative DG algebras. If they are quasi-isomorphic as associative DG algebras, then they're also quasi-isomorphic as commutative DG algebras. So that's the first main result. And the second main result is Kosul dual to this one. And I think I should say something about what Kosul duality is. One of the reasons is that if you try to learn Kosul duality, one of the things that strikes you is that there are 1,000 different things that are called Kosul duality. And they seem to not be the same thing, but apparently they are the same thing. But I guess this is a well-known phenomenon in physics as well, that there are supposed to be these dualities, and that duality is the same as that duality, and you look at it and you don't understand that. So this is somehow a simple-minded thing. So there are these functor that takes from a DG Lie algebra, a commutative DG algebra, and backwards. And that's a Kosul duality, and it interchanges Lie algebras and commutative algebras. And there's a closely related set of functors that goes from associative algebras to associative algebras. So the Kosul dual of a Lie is a commutative thing, and the Kosul dual of an associative thing is an associative thing, and so on. And the easiest instance of this is something that all of you are familiar with. So if I start with the Lie algebra, and I want to know what is its Kosul dual, that's supposed to be some commutative DG algebra, it's the Chevalier-Eilenberg cochain algebra. So I take my Lie algebra, I dualize it, degree shift, take the exterior algebra. And now the bracket on G defines a differential on this construction. That gives me a DG super commutative algebra. And the other functors in this diagram are very, very analogous to this one. You have to dualize, degree shift, and take the free object. So here I'm taking the free commutative algebra, that's this exterior power. But in this case, I would take the free associative algebra, which is a tensor algebra instead of the exterior algebra. And in all these cases, the product on one side becomes a differential on the other side, and the equation d squared is 0 translates into associativity or the Jacobi identity. In Koszul duality, it also has the property that it interchanges the two functors between these things on both sides. So there's a functor from Lie algebras to associative algebras. This is universal enveloping. There's a functor from commutative algebras to associative algebras, which is forgetting the fact that my algebra is commutative. And Koszul duality swaps these two functors with each other. So now if I tell you that our second theorem is Koszul dual to theorem A, you can almost guess what the statement is. The statement is that if I have two DG Lie algebras concentrated in positive or negative homological degree, and I assume that their universal enveloping algebras are quasi-isomorphic as DG algebras, then G and G prime are also quasi-isomorphic as DG Lie algebras. And I should comment on this. We have a paper on the archive. On the archive, this restriction does not appear, concentrated in positive or negative homological degree. We stated for unbounded DG Lie algebras. Now I just want to state it in this way. We found a gap in our argument 2 weeks ago. Such is life. We're working on trying to fix it. But we need we need to bend over backwards at some point here. So there's this thing with Koszul duality. It's not a perfect duality. You always lose stuff when you go from one side to the other. And we thought that we had taken sufficient care, but apparently we hadn't. So this version of theorem B does not resolve the motivating question that I started with, because classical Lie algebras concentrated in degree 0 is just completely ruled out here. I have to be in positive degrees or negative degrees. There's a variant version of theorem B, however, which looks like this. So here I have K and K prime that are now Lie co-algebras. And then the claim is that if they're co-enveloping co-algebras are weakly equivalent as co-algebras, then K and K prime are also weakly equivalent. That sounds a bit more exotic. Weak equivalence is stronger than quasi-isomorphism. I don't want to say too much about this. But this version does imply a positive answer to this motivating question if I'm finite dimensional. So that resolves this open problem in the finite dimensional case. And why does it imply this? Well, if I take the linear duals of G and G prime, then I get a Lie co-algebra, and I can apply this theorem to it. But in general, for an infinite dimensional thing, the linear dual is not a co-algebra anymore. You can always dualize a co-algebra to get an algebra, but only under finite dimensionality can you dualize an algebra to get a co-algebra. So right now we can prove this theorem B in the positively graded and the negatively graded and finite dimensional concentrated in degree 0. We'll see if we can do the other cases too. Yeah?
There's no necessity to precise in which way they're isomorphic.
What?
Here is you mentioned the universal enveloping coalgebras.
Yes.
You said they are isomorphic. Is it self-evident in which way?
Maybe this is what you're asking about. So before I talked about quasi-isomorphism, and now suddenly I have isomorphism. And if I have something with no differential, then quasi-isomorphism and isomorphism are the same thing. Because if I have quasi-isomorphism, that means I become an isomorphism when I take homology. And if I have no differential, then taking homology does nothing.
Earlier you mentioned you might wonder whether it has to be algebra or as...
Oh, yeah. Right. Oh, I see. Right. So in this corollary, UG and UG prime are isomorphic as associative algebras. not as bialgebras, so this does answer this problem. So some previous work that was important for us is due to Bashar Saleh, and he proved this two special cases of these two theorems, and he did the case when A prime is the homology of A, and the case when G prime is the homology of G. So in his paper, the statement would be that A is formal as a commutative DG algebra if and only if it's formal as an associative algebra. And G is formal. Oh, this is supposed to be that G prime is H of G, not H of G prime. Yeah, so you can detect formality on the level of the universal enveloping algebra, and you can detect formality after forgetting the commutativity. And our starting point was trying to see how understanding what is the right setting to understand these results. And the question of whether you can recover a Lie algebra from its universal enveloping algebra is analogous to a more well-studied question, which is about if you have a group, can I recover it from its group ring? And it's exactly the same thing here. If I know the group ring as a bialgebra, I can take the group-like elements and I get the groups immediately. But then I can ask, well, what if I don't have the bialgebra structure, I just have the associative algebra structure? Many papers were written about this, and then at some point the whole subject was killed because Martin Hertwig constructed this example proving that nothing you expect to be true can be true. So you can have finite groups. The integer group algebras are isomorphic as associative algebras. It's still not true that G and H are isomorphic. So as I briefly mentioned, our original motivation was rational homotopy theory. So why does this have anything to do with that? So Sullivan, in 1977, he constructed a functor from spaces to commutative DG algebras. And this functor was called APL, piecewise linear de Rham forms. And what he proved about this functor is, first of all, that this APL of X is quasi-isomorphic to the cochains on X, with the Q coefficients, as associative DG algebras, not as commutative DG algebras. And it wouldn't even make sense for this to be a quasi-isomorphism as commutative DG algebras, because it's well known that these cochains do not actually commute. Cochains are not commutative. They're like Steinrod operations. Well. And he also proved that these two spaces, X and Y, have the same rational homotopy type if and only if these two commutative DG algebras, APL of X and APL of Y, are quasi-isomorphic as commutative DG algebras. Now it's a very natural question to ask, can I detect the rational homotopy type without using this functor APL? Can I read off the rational homotopy type only from the cochains? The cochains are a lot easier to write down than an APL. And our theorem plus Sullivan's results right here says that X and Y do have the same rational homotopy type if and only if the cochain algebras are quasi-isomorphic as DG algebras.
Does that also follow for knowing that the true isomorphism is
No. Well, from that statement you would deduce that if you have this as E infinity, then X and Y would have the same rational homotopy type. But here the assumption is just that these are quasi-isomorphic as DG algebras, E1 algebras. And promoting that to an E infinity isomorphism is just a reformulation of what we're doing here. So this was a folklore open problem in rational homotopy theory. And before Sullivan did his work on the rational homotopy theory, there was Quillen. And Quillen worked not with commutative DG algebras, he worked with DG Lie algebras. So Quillen did things exactly causal dual to Sullivan. And theorem B also has a rational homotopy theory interpretation. So Theorem B combined with Quillen's work on rational homotopy theory says that X and Y have the same rational homotopy type if and only if the chains on the loop spaces of X and Y are quasi-isomorphic as DG algebras. So what Quillen did is he assigned to a space a DG Lie algebra, and he proved that if the two DG Lie algebras are quasi-isomorphic, then the spaces have the same rational homotopy type. Now the universal enveloping algebra of this Lie model that Quillen wrote down is itself quasi-isomorphic to chains on the loop space of X. So that's why you get this result from what Quillen did. Yeah, I'm cheating here. So for this, X and Y are supposed to be simply connected based spaces. I didn't say this. For this, X and Y are supposed to be connected nilpotent finite type. Right, and why is this an algebra? I'm taking chains, not cochains. I'm not supposed to be able to multiply. Multiplication is given by Pontryagin product. So I can concatenate loops, and I can make that strictly associative if I have loops with a length. And that makes this into an associative DG algebra. So I want to say something about what goes into the proof. And the first step is to forget about commutative DG algebras and to forget about associative DG algebras. So instead we replace them with A infinity algebras and C infinity algebras. And this makes life a lot easier. And why is that? Well, if I have a quasi-isomorphism between A and A prime as DG algebras, that's in fact equivalent to saying that there is a quasi-isomorphism from A to A prime in the A infinity world. So you remember this statement here that A is quasi-isomorphic to A prime, this was something about the zigzag. I could not deduce the fact that there was a map from A to A prime, but when you work with A infinity things, you always have a map. That's because every A infinity quasi-isomorphism has an A infinity quasi-inverse. So I can just invert all of the maps that go in the wrong way in the zigzag. And the same thing is true in the commutative setting. So these are quasi-isomorphic as commutative DG algebras if and only if there is a C infinity quasi-isomorphism between them. So that gives a reformulation of theorem A. If there is an A infinity quasi-isomorphism between two C infinity algebras, then there also has to exist a C infinity quasi-isomorphism between them. And this is completely equivalent to the statement of theorem A. So I don't think I need to say anything about what is an A infinity algebra in this room, but I should maybe say something about what is a C infinity algebra. So an A infinity algebra, well, okay, apparently I'm going to say something about what is an A infinity algebra. So mu1 is a differential, mu2 is a multiplication, the higher mu-n's are higher homotopies, making it associative up to coherent homotopy. And the C infinity algebra is an extra property on an A infinity algebra. So the C infinity algebra is an A infinity algebra with the additional property that mu-n vanishes on signed shuffles. So there's a shuffle product on the tensor algebra. I can put in a bunch of signs in the formula for the shuffle product, and the claim is that I'm supposed to vanish on anything which is a non-trivial product of two elements with respect to this shuffle product. And the easiest example is, what does it mean that mu2 vanishes on signed shuffles? It means that it's supposed to vanish on every element of the form x tensor y minus the Kosul sign rule y tensor x. And saying that mu2 vanishes on this element is the same as saying that mu2 is commutative. And then I also have this vanishing on shuffle conditions on the higher mu-n's as well. And that's somehow saying that the higher homotopies have to satisfy a partial commutativity condition, which when you just write it down like this, it doesn't look very natural, but it is natural. Some of you might know what an E infinity algebra is. I think E infinity algebras are more common than C infinity algebras. So I should comment on the difference here. An E infinity algebra has a multiplication which is commutative up to coherent homotopy and associative up to coherent homotopy. Here I have associativity up to coherent homotopy, but commutativity is strict. I'm saying that mu2 of x tensor y is literally equal to mu2 of y tensor x. There's no homotopies there. And in characteristic 0, C-infinity algebras are a nice alternative to E-infinity algebras that are easier to work with. But for many practical purposes, they do the same job. And I should also say something about morphisms between C-infinity algebras. So morphism of A-infinity algebras consists of maps like this from A tensor n to B. And similarly, I say that F is a C-infinity morphism if it vanishes on these sign shuffles. So being C-infinity is a property of a morphism. And in particular, if A and B are C-infinity algebras, then there are many, many more A-infinity morphisms between them than C-infinity morphisms. As we expect, otherwise this reformulation of the theorem would be trivial. The reformulation we got was that if there is an A-infinity quasi-isomorphism, then there has to be a C-infinity quasi-isomorphism. And for that to be a non-trivial statement, there had better be a priori many more A-infinity morphisms. Yeah, so that's what we gain here. We don't have to deal with zigzags, and we just have to look at A-infinity morphisms and C-infinity morphisms. There will be many more A-infinity morphisms, but if there is an A-infinity which is a quasi-isomorphism, then one of the C-infinity ones would be a quasi-isomorphism as well. Okay, so every A-infinity algebra is quasi-isomorphic to its homology, with a transferred structure of A-infinity algebra on the homology. And the same is true for C-infinity algebras. And this means that when we're proving theorem A, we might as well assume that they're both equal to their homology. We can just replace them with that before we do anything else. But we also assume that they are quasi-isomorphic, and a quasi-isomorphism from A to A prime will give us a canonical identification between these homologies. So I can actually assume that the homologies are the same. And then the statement of theorem A becomes the following. If I have two C-infinity algebra structures on the same graded vector space, right? Because I identify these two with each other. And there's an A-infinity isomorphism between them whose linear term is the identity map. Right? A morphism consists of these terms H tensor n to H, and the linear term is the one that goes from H to H, and it's supposed to be the one induced by this identification. So if there's an A-infinity isomorphism whose linear term is the identity, then there also is a C-infinity isomorphism of the same form. And an A-infinity isomorphism whose linear term is the identity is for some reason called an A-infinity isotopy. I have no idea who came up with this name. It seems to be standard. I hate it. Many people in the room know what an isotopy is. If someone of you can explain what this has to do with the notion of isotopy, I would be happy to hear it. Yeah, so that's the second reformulation of the theorem. And this now becomes tractable to writing it in terms of deformation theory. So I would say just tiny things about this. So it's this principle that was originally due to independently Deligne and Drinfeld. And it says that if you have a DG Lie algebra, you're supposed to be able to associate to that a formal deformation problem, and every formal deformation problem should come from a DG Lie algebra. That's the original principle. And I want to say just in a few words how this goes. And I will do the easy part, how to assign a deformation problem to a DG Lie algebra. The other direction is the harder part. So if I have a DG Lie algebra, I'm supposed to associate to it a deformation problem, and the solutions to this problem are solutions to the Maurer-Cartan equation, or master equation, in the DG Lie algebra. Degree minus one element satisfying this thing. Note here that I'm taking everything super commutative, so x bracket x is not necessarily 0. And I'm also supposed to have a notion of deformation equivalence of solutions. When can I deform one solution to another? And that's defined by the action of a group. And the group in question is given by taking the degree 0 elements. That's a Lie algebra, and you exponentiate that to get a group. And this group acts on the set of Maurer-Cartan elements. It's called the gauge group. And the solutions to the deformation problem is Maurer-Cartan, and the notion of equivalence is given by the action of this gauge group. There's something that needs to be said here. In general, I can't just exponentiate any Lie algebra and get a group. I need to put some kind of hypothesis there. And what you do is you say that, well, this group is actually only defined after I tensor this Lie algebra with a maximal ideal in a local Artin ring. And then it becomes nilpotent, and then the Baker-Campbell-Hausdorff formula converges, and I can exponentiate it to get a group. So that means, I should say here also, but maybe this was clear from how I said it, you can always tensor a Lie algebra with a commutative ring, and you still have a Lie algebra. So what you get from this construction is actually a functor that assigns to a local Artin ring a groupoid. The groupoid is a set of solutions to the deformation problem over that ring, and the notion of equivalence is this gauge group. And a functor from local Artin rings to groupoids is basically a formal stack. Or at least these kinds of ones are formal stacks, meaning a formal neighborhood of a point in a moduli space. And that's why I call this a formal deformation problem. It describes the formal neighborhood of a point in a moduli space. But this is in fact not what we do. So we will consider complete DG Lie algebras. So we impose the condition that we have a filtration, and that the Lie algebra is complete with respect to this filtration, and it makes all of the power series converge in the definition of the action of the gauge group and in the Baker-Campbell-Hausdorff formula. So there will be no Artin rings, and it's not really the same as this algebra geometric construction, but the formulas are identical. And now the point is that there is this thing called the deformation complex. So if I have a chain complex, I can associate to it a DG Lie algebra, which is complete in the sense that I just told you, def A infinity of V, and it has these properties. Maurer-Cartan elements, solutions to the deformation problems, are the A infinity algebra structures on V. And there's this notion of equivalence given by exponentiating the gauge group, and these gauge equivalences are exactly the A infinity isotopies. And that's a surprisingly recent theorem of Totsenko, Shadrin, and Valette. This deformation complex goes back to the very beginning of the subject. There are obviously two different groups that you can write down that act on the set of solutions. There's an obvious bijection between them, but then you actually have to prove that the group operations are the same. Like the Baker-Campbell-Hausdorff formula in one of them coincides with the sum over trees formulas on the other side. I don't think anyone had written this down before they did it. Well, and in this DG Lie algebra, there is a DG Lie subalgebra parameterizing C infinity algebra structures, where the gauge equivalences are instead of C infinity isotopies. And this leads now to a third reformulation. Oh, I should say this. So this DG Lie algebra that I just told you, it's more or less the Hochschild cochain complex of V. And that might be a surprising statement, because V here was supposed to be a chain complex. And the Hochschild cochains are defined for an algebra, but V is not an algebra. So to make this statement precise, you'd say that an A infinity structure on V is the same as a Maurer-Cartan element in this deformation complex. That's what I just told you. And whenever you have a Maurer-Cartan element in a DG Lie algebra, there's this construction you can do. You can add this term bracketing with mu to the differential, and you get a new differential. And the Maurer-Cartan equation is exactly equivalent to saying that this thing squares to 0. So if I have an A infinity algebra V, and I get this Markov-Cartan element, and I can look at this twisted differential on the deformation complex, and that thing is more or less the Hochschild cochains. Which makes sense. The underlying vector space of the Hochschild cochains doesn't see the multiplication, it's just the differential that sees the algebra structure. And I put this approximately here. I have to remove the Hom VV term here, and I have to do a degree shift. And there's a similar thing. This C infinity deformation complex is given by the Harrison cochain complex. So Harrison is like the commutative version of Hochschild. But now I can reformulate the question very generally. I can just ask about this. When I have a DG Lie subalgebra of some other algebra, when do I have an inclusion on solutions of this deformation problem? And here's a criterion that we prove. If both of these are complete and there is a retraction from G down to H, and that it's important that this G is a map of modules over the smaller Lie algebra. So it's supposed to be a homomorphism with respect to taking the bracket with anything in the smaller Lie algebra. Then this is injective. So that means that if we want to prove theorem A, it's clear what we have to do. We have to construct a retraction from the Hochschild cochains down to the Harrison cochains. That splits the natural inclusion of the Harrison cochains into the Hochschild cochains. And the good news is that this was constructed in 1968. So Barr proved that Harrison cohomology always injects into Hochschild cohomology over a field of characteristic 0, and the way he did that was by constructing exactly such a retraction that we need. So that proves theorem A. And since I have some time left, I want to say something about, well, first how we prove this result. So we consider G and H and R as before, meaning that G is a DG Lie algebra, H is a DG Lie subalgebra. They both have complete filtrations. R is a map of H modules down from G to H, which splits the inclusion, and R itself preserves the filtration. And now I take two Markov-Cartan elements in the smaller one, and I assume that they go to the same thing in the Markov-Cartan set of the bigger one, meaning that there is a gauge in the bigger one that takes one from the other. And I want to prove now that there's also a gauge in the smaller DG Lie algebra. And I find this gauge by solving a fixed point equation. So I define inductively a sequence of elements like this. I start with A and X, and I iterate this procedure. And you have to do a calculation to see that the limit of this sequence of element xn is y. The limit of this sequence r applied to an is 0. And you see here that r of an is what takes xn to xn plus 1. Now the fact that this limit is 0 means that I can make sense of this infinite product. The terms here go to 0. And now r of a1 takes x0 to x1, r of a2 takes x1 to x2, and so on. So this product takes x to the limit of all of these xn's, and that's y. So it's a gauge from x to y. And I want to draw a picture that explains something of this formula. So I have x here, I have y over here, and x is x0, and I have a gauge like this. So what's the first step in this iteration? I replace x by x1, which is given by taking x, and I act by the projection of A down to the smaller Lie algebra. So I have A over here, and I project it down to the smaller thing. And now it no longer has any reason to be a gauge from x to y. It's just going to be a gauge from x to some other element. It goes like this. And here I have RA0. And what is now A1, it's given by the Baker-Campbell-Hausdorff formula of A0 and then minus R of A0. So it's going backwards along this arrow and then forwards along that arrow. So this is my A1. And now I'm supposed to iterate this procedure. So before I had X and Y and I had an arrow between them and I did this thing. And now I have instead X1 and Y and I have this arrow between them and I do the same thing. So I go from X1 to X2. I have an arrow here which is R of A1. And you see the point here is that at each step, these xn's are moving closer to y. They're going to be one step closer in the filtration that I wrote down. So as n goes to infinity, these points are going to end up closer and closer, and they're going to converge to y. And these arrows are similarly going to converge to something. But it's not these arrows that I care about. It's these blue ones whose length goes to 0. And I can compose all of them because of the lengths going to 0. And I get a gauge from x to y down here. And the proof of these claims that this limit is y and this what you have to do is say that it's an induction argument. At each step, this moves closer to here than it was before with respect to the filtration. This thing becomes closer than the previous one with respect to the filtration. And since you're always working modulo higher terms in the filtration, you can actually set all of the commutators in the Baker-Campbell-Hausdorff formula to 0. You can set the formulas in the gauge action, all the commutators are 0. So it becomes a really easy calculation. And I also want to say something about how you deduce theorem B from theorem A. And it's about this Koszul duality. So these functors that occur in the Koszul duality, I denote them B and omega and C and L. And well, before I was talking about the Koszul duality as being a duality between Lie algebras and commutative algebras, but the better behaved one goes between Lie algebras and co-commutative co-algebras. I don't have to do this dualization in the Chevalier-Eilenberg. So I suppose that I have two Lie algebras, and their universal enveloping ones are quasi-isomorphic. Then I first replace G by its bar-co-bar resolution. So G is the same as L of C of G up to quasi-isomorphism. And then I say, well, I have this intertwining between universal enveloping algebra and the forgetful functor. So the universal enveloping algebra of the Lie functor is the same as the co-bar functor. This is actually the same as a co-bar of CG is co-bar of CG prime. But now I can apply the bar functor to that. So here I get bar omega CG is quasi-isomorphic to bar omega CG prime. And bar co-bar of something is the same as the thing. So that CG is quasi-isomorphic to bar omega bar o bar. This is a zigzag of quasi-isomorphisms of DG co-algebras. But now I'm in a situation exactly dual to theorem A. Here I have two co-commutative co-algebras. I have a zigzag of quasi-isomorphisms of co-associative co-algebras. And by a dual form of theorem A that you prove in the same way, you deduce that CG and CG prime are actually quasi-isomorphic as co-commutative DG co-algebras. And then you apply the functor L, and then you get that G is quasi-isomorphic to LCG, which is this. The G and G prime are quasi-isomorphic. And the tricky step here is the last step. This functor L does not preserve quasi-isomorphisms in general. And that's why you don't have this perfect duality. So if you're positively graded or negatively graded, then L does preserve quasi-isomorphisms, and the argument that I just showed you goes through. If I work with weak equivalences, which are stronger than quasi-isomorphisms, the argument goes through. And what our idea here was that, in fact, all of these are filtered quasi-isomorphisms, and for filtered quasi-isomorphisms, you also know that co-bar preserves quasi-isomorphisms. But these are filtered quasi-isomorphisms with respect to different filtrations. So when I make an A infinity quasi-isomorphism out of the zigzag, that thing is not going to preserve any filtration at all. And that's the error in our paper. If you have any idea how to fix that, I'd be happy to hear it. Tack.
Okay, we have time for some questions. Wait, can you wait for the microphone? No, we don't want to lose the philosophical question for posterity. So,
maybe not so philosophical. So the fact that the Harrison Harrison homology embeds in the Hochschild homology, that's more or less the infinitesimal version of your result. I mean, it says deformations of one kind.
Yes.
So I could imagine that it's not so difficult to prove. I mean, essentially what you're saying is you can integrate that, and I could imagine that's not so difficult to prove under any sort of hypothesis about, positive gradings or negative gradings or something. But why is it that you're able to integrate that statement without such hypotheses?
Yeah, I'm not a philosopher. I mean, you're right that there's a process that has to converge here, but the convergence is not taken with respect to the grading; it's taken with respect to this length filtration of the Hochschild complex. I don't know if that helps.
Okay.
There's a question right here. She's coming the other way.
Well, it's a similar, not philosophical, but maybe historical question. I think the original, at least, statement of the homotopy transfer theorem requires some boundedness as well, right? Kadishvili theorem. And you need to be able to start. It has to be K-projective or something like this.
Yeah, in Kadishvili's original paper, there is no boundedness assumption. It's just that the homology is free or projective. And that's enough.
Are there any further questions? Well, if not, let's thank the speaker again.